Attention projectionists. This chart will help you make sure that your picture will be focused properly before the show starts. Adjust the lens so that the bells in the corners and the two words are all sharply focused. Now adjust the sound volume. That's all. When this bell system seal fades out, shut off the projector. Everything will be properly set for your show to begin.
This is a man-made mechanical mouse trying to find its way through a maze. It tries various directions one after another, and when it discovers an open path, the mouse moves forward until another barrier stops it. Then it probes for another opening, eventually working its way by trial and error through to the goal. The remarkable thing about this mouse is that once it has found a way through the maze, it remembers the route it took. So if it is set down at the start again, it can run through the maze directly to the end without a mistake. The ability of this mechanical mouse to learn and remember information lies in its brain of switching relays and circuits. Similar circuits and concepts were used in designing other thinking machines, such as this modern electronic computer, which can solve mathematical problems with a speed and accuracy that humans cannot hope to match. To be able to do this, a machine must, like the human mind, have some means of storing information and referring to it when needed. This film will show some of the storage devices used in machine memories and explain how information is stored in them. The information coming out of this computer is in a human language, expressed in the letters of the alphabet and the numbers of the decimal system. But internally, most computers use a simpler language consisting of just two symbols, 0 and 1. The presence of one or the other of these binary digits constitutes an elementary unit of information called a bit. By combining bits in various patterns, different items of information can be represented. Binary codes, of which there are many variations, are particularly suitable for use in machines because the binary symbols can be represented by physical devices. This extremely simple example can represent the bit symbol 0 when open and 1 when closed. Or a capacitor can be thought of when charged as storing a 1, when uncharged a 0. And a light may represent a 1 when on, and a 0 when off. So simple bit information can be stored in almost any device if the device can exist in either of two stable states. Several on-off devices are needed for storing more complex information. A combination of bits stored in memory devices is called a word. Bits can be written in or read out of a memory one at a time, or all the bits of a word can be stored or read out simultaneously. More than one row of binary storage devices is needed when more than one binary word of information is to be stored. In this array, a different word can be written in each of the rows. The position in the memory bank where a bit is stored is called its address. There are two methods of getting to a particular address. In the sequential access method, devices are scanned in order, one after another, until the desired address is reached. This method is slower than the random access method, in which any cell is reached directly by entering the array in two coordinate directions simultaneously. The cell at the intersection is the desired address. Different methods of access are used by different types of memory devices. The punched card stores information in a pattern of holes and no holes, which can represent a code of binary ones and zeros. Each vertical row constitutes one binary word, which is punched into the card simultaneously. The standard card holds 80 words of 12 bits each. With stacks of cards, a machine forms its library of memory of virtually unlimited capacity. Machines read this information sequentially with metal probes at about 200 cards per minute. Diverse kinds of information, such as a corporation's payroll or calculations of a satellite orbit, are stored permanently on punched cards, which end to end show their similarity to the punch tape, also a mechanical storage device. This tape has space for 8 holes or no holes across it, plus a small sprocket hole which serves to advance it through the machine at about 10 rows per second. One 8-bit word is stored in each row, and access for writing or reading the words is sequential. In the teletype machine, a tape with only 5 hole positions is used. One binary word, representing a letter or numeral, is written onto the tape every time a key is pressed. And still another punch tape makes a mechanical record of telephone calls for accounting purposes. Telephone systems also use electromechanical memory devices. Banks of relays store temporarily routing directions for a telephone call. Simple and faster than the punch card, access to a stored bit takes less than 1/100th of a second. 5 relays using a variation of binary representation called 2 out of 5 are used to store each digit of a telephone number. The relays are designated 0, 1, 2, 4, and 7. 2 relays are operated at one time for each decimal digit. Dialing the number 3, for example, will operate relays designated 1 and 2. If by chance only one relay operates, the system knows there is an error. From here, the digit is transferred to a package of 5 simple relays. 2 out of 5 code is used here also. Each telephone digit dialed is stored in its own package of relays in a bank. This information is used to control the crossbar switch, which completes the telephone connection. Electromechanical relays are reliable memory devices, but they require considerable space. Modern electronic computers use a more compact memory based on magnetism. On these reels is half-inch mylar tape coated with a magnetic material. The magnetic tape is like the punch tape, only instead of holes, it stores information in patterns of small magnetized spots. A row of 7 tiny electromagnets called heads record a 7-bit word across the tape. The pattern can be seen on this piece of tape that has been dusted with a fine iron powder. A spot represents a 1, no spot represents a 0. The bits are read a row at a time. As the tape passes over the heads, a magnetized spot will induce a pulse of current in a head. When there is no spot, there will be no readout current. Bits are read or written only while the tape is moving. Since time is needed to position the tape from one address to another, this sequential access is comparatively slow. However, storage capacity can be very large. The same information requiring thousands of punched cards can be stored on a single roll of magnetic tape, and the number of tape rolls is unlimited. The magnetic drum may be thought of as a number of magnetic tapes fastened side by side to the surface of a cylinder. Actually, the drum's surface is coated with a magnetic material. As the drum rotates, electromagnetic heads record bits in the form of magnetized spots in parallel tracks around its circumference. This drum can store 1,000 words of 20 bits each. It rotates at about 24,000 RPM. A pulse of current sent through a head will magnetize the surface directly under it, thus recording a binary 1. Current in the opposite direction will magnetize a spot in the reverse direction and record a binary 0. In this simple drum, reading is accomplished as a magnetized spot passes under a head. Its direction of magnetization is sensed, and a voltage pulse of appropriate direction is passed on to the readout circuit. The drum rotates continuously, and readout is continuous except when a head is being used to store a bit. But writing and reading must wait until the desired storage cell comes opposite a head. Even with the fastest rotating drums, this waiting time may be 1/1000th of a second. Larger drums are able to store many more bits, but cannot be rotated as fast. So this drum, which stores more than 8,000 17-bit words and rotates at 12,000 RPM, uses many rows of heads to reduce access time. Nevertheless, the sequential access of a magnetic drum is a shortcoming, and another magnetic storage device, the magnetic core, has been developed, which uses the faster random access method. The core is molded from powdered ferrite with a binder in the form of a tiny ring. It is useful as a binary memory device because it can be magnetized in either of two states. When a conductor threaded through the core is pulsed with a current, the core becomes magnetized and will remain magnetized until a pulse in the other direction reverses its magnetic state. The square hysteresis loop of ferrite illustrates what happens. Once a core is magnetized to saturation, it will retain almost all the flux, even after the magnetizing current is removed. Applying a large magnetizing current in the opposite direction will reduce the flux past the knee of the loop and saturate the core rapidly in the other direction. The core will remain magnetized after the pulse is removed. Thus, the core is always magnetized in one of two stable states, which can be designated 0 or 1. Note that a weak magnetizing pulse is not strong enough to switch the core's state. This characteristic is utilized in core arrays in which many bits are stored in many cores strung on a matrix of wires. The memory is designed so that when weak current pulses are sent through X and Y wires simultaneously, at the intersection their magnetic fields combine and are strong enough to switch the core. The other cores in the array do not receive sufficient field and remain in their original magnetic state. For reading the stored bit, a third wire is needed, linking all the cores of the array. To read, the X and Y wires are pulsed in the opposite directions to writing. If the field at the intersection opposes the core's magnetization, the core will switch, inducing a voltage in the readout wire and indicating that the core contained a 1. If the field at the intersection is in the same direction as the cores, little or no voltage is induced in the readout wire, indicating a 0. It's apparent that the read pulse will erase the information held by a core, so a regenerating circuit automatically rewrites a bit after it has been read. A bit can be read out and rewritten in about 10 millionths of a second. To store words in a core memory, several planes of arrays like this are stacked in parallel. This computer memory stores almost 7,800 24-bit words. The X and Y wires pass through the cores, joining the planes in series. Pulsing an X and a Y wire will store a 1 in one core in each plane. For storing zeros, inhibit wires on each level are needed. A pulse sent through one of the inhibit wires in the opposite direction and at the same time as pulses in the X and Y wires will prevent a core from switching, thus storing a 0. Each plane has its own readout wire. When simultaneous X and Y pulses cause a core to switch, a signal will appear. Thus, the bits of a binary word are read out simultaneously on all readout wires. Stacks of core arrays in large computers can store 1,000,000 bits or more. Ferrite cores are usually very small because how fast a core can be switched depends, for one thing, on its size. Odd-shaped cores with 2 and 3 holes and extremely fast switching times have been developed. This one with 3 holes is called an inhibited flux core. It's used in a memory which can store 40 28-bit words. The X, Y, and readout wires are each threaded through individual holes. This memory is extremely fast and has a read-write cycle of only 2/millionths of a second. The Ferrite sheet memory uses the same magnetism principle as the core array. In this thin sheet of ferrite, the areas immediately surrounding the small holes act as cores and store bits by being magnetized in one of 2 directions. One long conductor is electroplated onto the sheet, lacing in and out of the 16 by 16 array of holes. This is the Y wire. To form a memory, 24 sheets are stacked in a frame. Then thin copper wires are threaded through the holes in all sheets, forming 16 parallel planes of inhibit wires. Then the stack is joined to another stack by threading 16 planes of X wires, making a module of 256 48-bit words. Modules can be interconnected to form larger memories, such as this 50,000-bit one. It takes only 1/4 the space and costs about 1/10 an equivalent core memory. Magnetic storage is also the principle underlying the twister memory. The twister gets its name from this ribbon of magnetic material, which is wrapped 100 turns per inch around an insulated copper wire. The ribbon is only about 1/3 of a mil thick, and the wire has a diameter of less than 3/1000ths of an inch. In this particular memory, 26 twister wires are embedded in a plastic sheet and mounted in a frame so as to pass through 32 solenoids. In this simplified diagram, pulsing simultaneously on one solenoid and some of the twister wires will store bits in the helical ribbon at the intersections. Here's what happens. Limited pulsing on a solenoid will create a magnetic field through it that has a component in the same direction as the helical ribbon. Since the pulse is limited, the field will not be strong enough to magnetize the ribbon under a coil unless it is aided by a simultaneous pulse on a twister wire. The resulting magnetization of the ribbon represents a 1. Where the coil intersects an unpulsed twister, the ribbon will remain unmagnetized, representing 0. For reading, a large pulse is sent through a solenoid in the reverse direction. This reverses the flux in the ribbon where 1s are stored and causes simultaneous readout pulses on the twister wires. Absence of a readout pulse indicates that a 0 had been stored. This buffer memory has a capacity of 32 26-bit words. For larger capacity, another type of twister memory has been developed. Instead of coils, the solenoids are copper bands, which are embedded in plastic and folded over the sheet of twister wires, forming a coordinate grid. Bits are stored at intersections as before. 16 similar grids are made along a continuous sheet of twister wires, which is then folded into a stack of planes. This 3-dimensional array can store about 15,000 bits with an access time of only about 5/millionths of a second. The twister stores information temporarily. A permanent memory has been developed which uses the twister as a reading mechanism. On these cards, binary information is stored by the presence or absence of tiny permanent magnets. The cards are inserted in a twister module. When currents are applied, the presence of a magnet at an intersection inhibits the twister segment from switching. Where there are no inhibiting magnets, the twister segments do switch, thus reading out the permanent data stored on the card. Another simple permanent memory device stores bits by the presence or absence of small capacitors in a grid-like array. On a plastic sheet, rows of copper spots connected horizontally by electrodes are printed by an etching process. Then a thin sheet of non-conductors such as mylar is placed over the array, and another array of copper spots connected vertically by electrodes is matched over the first, forming a grid of small capacitors connected by coordinate electrodes. The presence of a capacitor cell at an intersection can be thought of as representing a 1. By cutting the electrode leading to a capacitor, the cell can be made a permanent representation of a 0 bit. To read the stored information, a voltage is applied to a horizontal electrode. A voltage appearing on a vertical electrode indicates a 1 is stored, and the absence of a voltage, a 0. Access time for reading a stored word is less than 3/millionths of a second. This sheet contains 18 by 32 positions and is stacked with other planes to store 3,000 18-bit words. Capacitance is also the underlying principle of the barrier grid tube. This one stores over 16,000 bits with an amazingly fast access time of about 1/millionth of a second. Basically, it's a special type of cathode ray tube. The electron gun shoots a beam of electrons between deflection plates at the storage target, which consists of 3 elements. A very fine tungsten wire mesh from which the barrier grid tube gets its name, a mica disc on which bits are stored in the form of electrostatic charges, and an aluminum backplate which controls the relative potential of the grid and the mica. In this cross-section view of the barrier grid, the mica, and the backplate, we see that when negative potential is applied to the backplate, the grid becomes positive with respect to the mica. The high-velocity electrons of the beam pass through the grid, strike the mica, and dislodge more electrons from the spot than are arriving via the beam. The dislodged electrons are attracted to the positive grid, resulting in a net loss of electrons on the mica, in effect, a positive charge. When the beam and backplate potential are removed, the charge remains on the spot representing a binary 0. If a positive potential is applied to the backplate, the grid becomes negative with respect to the mica and will repel many of the dislodged electrons back to the spot on the mica. These, with the electrons arriving via the beam, will build up a negative charge on the spot, which when the beam and potential are removed will remain, representing a binary 1. The beam can be directed quickly to any spot on the mica at random, thus storing a pattern of negative and positive electrostatic charges representing 1 and 0 bits. They are read when the beam is directed to a specific address. If excess electrons are present, they are driven off through the grid to the conical collector. This produces an output signal indicating that a binary 1 had been stored. If the spot has a positive charge, the amount of electrons driven off will be smaller, and the collector current will be less, indicating a 0. A regenerative circuit is needed to restore bits that have been erased by reading. Bits are stored on the mica surface one at a time. Successive bits may represent a word, which may be read and regenerated by directing the beam to the address of the first bit and scanning succeeding positions. Sometimes several tubes are connected in parallel, so that one bit for each word is at the same address on each mica surface. The barrier grid tube is an extremely fast temporary memory. However, the principle of the cathode ray tube has also been applied to a permanent information storage called the flying spot store. It's truly a photographic memory. On glass photographic plates, in each of 68 square areas like these, 65,000 tiny transparent or opaque spots are photographically printed. The spots provide yes-no answers when swept by a moving pinpoint of light from a large cathode ray tube. The electron beam is directed to one address position on the face of the cathode ray tube. Lenses focus this spot simultaneously onto the same address in all of the storage areas. The light is stopped by the opaque addresses and allowed to pass through the transparent addresses, through another set of lenses, onto a bank of 68 photocells. These detect which areas allowed the beam to get through and which did not, thus reading out simultaneously one word of up to 68 bits. Still in the development stage, the flying spot store will provide access to its permanent memory of 5 million bits in a few millionths of a second. Extremely fast access times and large capacity like this have been the goals in the evolution of all types of memory devices. From the first, scientists and engineers have tried to develop faster, more reliable, cheaper machine memories with larger capacities. We have seen a few of the principal types. Each has certain attributes which make it suitable for a particular job. And since no one device is ideal for all applications, scientists are continually investigating new techniques and new materials, ever seeking new knowledge as they search for better storage devices for machine memories.